Everyone knows water and electricity don't normally mix, but combining them may be the key to harnessing the full potential of renewable energy. 200 years ago, we learned we can split water using electricity into hydrogen and oxygen gases. Hydrogen stores this energy in a chemical bond, which can be converted back into electricity using a fuel cell, with water being the only waste product. For this reason, hydrogen has been seriously considered as the energy carrier for storing renewable energy when the sun isn't shining or when the wind isn't blowing. The problem with storing hydrogen is that it's difficult. It is the smallest molecule possible, and it can pass through the gaps between atoms in common materials like steel. It also explodes in air. And as we don't want to repeat at the Hindenburg, we need a reliable hydrogen storage system. You could store it as a gas under high pressure, or as an extremely cold liquid. But the preferred option going forward is to store hydrogen in a stable, reversible chemical bond. One material that is naturally good at this is magnesium. It can store enough hydrogen to power a car, according to the US Department of Energy. Magnesium does have its drawbacks, however. It has to be heated to a high temperature to release the hydrogen it absorbed, and it does this really slowly. I'm working with a new class of magnesium alloys that has the potential to improve the release of hydrogen through a unique atomic arrangement called long-period stacking ordered structures, or LPSO. These structures form in magnesium when additional elements like zinc and yttrium are added in the right combination. LPSO is a stacking of layers, where nanoscale bands contain these added elements, which is unusual because most alloys don't form such a consistent, repeated chemical order. These additional elements are known to improve the release of hydrogen at lower temperatures, and the nanoscale bands help promote the movement of hydrogen in the metal once the bond is broken. In other words, these alloys have the right qualities to improve hydrogen storage simply due to LPSO's natural structure. My research is specifically exploring how the type and amount of additional elements added to magnesium create how much of this layer structure forms, and in turn, how this influences hydrogen's release rate and release temperature. By the end of my PhD, I will show the true potential of LPSO as a hydrogen storage material. I truly hope that my work holds water, or at least a small part of it. Thank you very much.